For the first lesson in the second half of this unit, we're actually going to revisit the beginning part of this unit and kind of start fresh. After hammering out some hardcore Algebra 1 at the beginning of this, when we did the first part of Topic 1, which is actually the last part of Topic 1, we're going to focus now, though, on some key features of our functions, both in equation form and in graph form. And in order to do that, we're going to kind of lay out some ideas as far as how to describe our graphs over a certain range, all right, over a certain interval of x values and a certain set of outputs to y values. And so in order to do that, we're going to kind of lay some groundwork today. So there is some functional stuff that we'll ask you to do, but then we'll apply that in our next lesson, 1.1 Part 2. All right, so here is just thinking about intervals and inequalities. We use them all the time to describe a set of values. So for example, the US voting public are those citizens who are 18 years old or older. Those are the people who are allowed to vote. And writing this as an inequality, not a new concept. X is greater than or equal to 18. If we were to graph that, we would draw a number line. We'd have 0 years of age, we'd have 18 years of age, and we can include 18 with a filled in circle, but then we would shade to the right, saying, hey, we'll take all the people who have this many years or more. Now, obviously, people don't live forever, so this doesn't really go on forever, but just thinking of the understanding of a set of numbers that is bigger than or equal to 18, we would understand that this number 18 is kind of a floor. And we would look for values that are bigger than 18, but less than infinity. We could never actually reach infinity. And so when we're dealing with set builder notation, we're going to use the inequality that puts x between two values, one of which may be positive infinity or negative infinity, or they could both be legit numbers. But the added part to the set builder notation is not just the inequality form, but to recognize that x is going to be a value for which 18 is less than or equal to x is less than infinity. We will never have less than or equal to with infinity because we will never equal infinity. There's always more there. So set builder notation actually looks like this. When we're referring to interval notation, we're talking about x being a set of numbers that is going to be including 18 and going to positive infinity. We'd have a bracket for the minimum value and a parenthesis for the infinity. Obviously, if we just went from like, well, you can't vote if you're over 60 or something like that, then we would have 18, 60, and we'd have brackets on both sides. And so there's different ways in which we can write our notations, whether we're using set builder or interval notation. We want to do a good job in articulating these relationships. So here's a situation where we have the inequalities drawn up. We have the word form of this inequality, the graph form of the inequality, the set builder notation, which was the last column, and the interval notation, which was the second to last column on the last slide. And what we're going to do is just kind of mess with that a little bit. So x is less than 3. We're talking about all of the values that are to the left of or less than 3. All real numbers that are less than or equal to 3 would be the filled in value and shaded to the left. All real numbers that are greater than 3 will have 0, we'll have 3, and we'll talk about all the numbers that are bigger than 3, we'll be shading to the right. And again, I don't care if you do it on the number line or above the number line, it doesn't really matter, as long as your circle is open or closed appropriately so. And x is greater than or equal to 3. Again, we've got 0, we've got 3. We are going to include 3, so filled in circle, and then fill in all the values that are bigger than the 3. So we want to make sure that you can do the Algebra 1 and the pre-algebra of the graphing, reading the inequality. But what's actually new, so I don't actually care if you write this down, I don't care about this column so much, but have the graph, have the inequality. But then when we do set builder notation, we want to make sure that we understand that we are talking about x values for which we have negative infinity less than x less than 3, where we have x such that we have negative infinity is less than x, which is less than or equal to 3, where we have x such that we go from 3 being less than x, which is less than infinity, and then also have values of x for which 3 is less than or equal to x, which is less than positive infinity. So we want to make sure that you can do that set builder notation, right? That you can write the inequality with those braces around it. When we're talking about interval notation, that again is where we say we are not counting the value of 3, so we're going to get close to it but not actually touch it. Or we go from negative infinity to positive 3, but we do include it. We have a bracket. We go from 3 up to positive infinity. We can never include infinity because we'll never equal it. Or we go from 3 inclusive all the way up to positive infinity exclusive. So inclusive versus exclusive. When do we use the parentheses versus when do we use the bracket? Keep in mind those setups. Now I'm going to do a couple of these, but then I'm going to ask you to do a couple of the others. Again, you do not need to have the word column written. I believe that you can read those. If you know that you can't understand what these are saying, then please write it out with words. But if you get that, then I'm assuming that you can read this. And then same with the graphs here. I'll fill in a couple of these graphs and then I'll do the notations over here. So the notation here, we go from negative 3, but inclusive, filled in circle, to 4, also inclusive, and we're going to be shading in between. So we're going to bold that in between negative 3 and positive 4. If I'm going to write that in interval notation, then I would write negative 3 in a bracket, positive 4 in a bracket. Negative 3, comma, positive 4. If I wanted to write this, again, we would go from negative 3 to positive 4, open because it excludes negative 3, but closed over here because it includes positive 4. We want to keep in mind the inclusive versus the exclusive. I'll do set builder over here, and then you can fill in the gaps. I just want to make sure that this fits on the screen. I've got x such that negative 3 is less than x, which is less than or equal to positive 4, and put the bracket around that. So we want to make sure that you are good on listing those set builder and interval notations, even if it doesn't include an infinity, even if it's just from an actual set of real number values. Please let me know if you have any questions on filling out the rest of this table. Draw those graphs, set builder, interval, interval, so that we can hammer those out well. Add that to your notes so that we can have that conversation. The last thing I want to show you is when we are referring to all real numbers. A lot of times when we're talking about the domain or the range of a function, we may include all real numbers for x or all real numbers for y. And how we want to approach that is on the number line, obviously, we're talking about all real numbers. So we would shade in the whole dang thing, and we would include arrows to say this is going to go on forever. Set builder notation, there's a couple different ways we can do that. We can say that we go from x, going from negative infinity is less than x is less than positive infinity. On interval notation, we can't include infinity, so we'll have the parentheses there. Another way that you can do that is to say that x is a member of the set of all real numbers in these braces, to say that we have that set notation. If it's all real numbers, then you can avoid writing an inequality or avoid using infinity and then just say, hey, it's all real. So it's a capital R and you draw kind of another line through it to communicate that script, all right, that we're talking about all real numbers. So all real numbers is obviously something that we'll explore when we look at the domains and range of these graphs. So what we want to be able to do, and I'll do a couple of these, I don't want to do all of them, but maybe I'll end up doing all of them, and we'll see. If we're talking about all the values of x that are less than 2, we're going to go from negative infinity to negative 2, parentheses, because we're excluding. This includes the 4 on the high end. It excludes the negative 1 on the low end. This goes from 2 exclusive to infinity exclusive. This goes from negative 6 inclusive to 0 exclusive, because it's an open circle there. So make sure that you have these examples drawn, and the interval notation. When we do example 2 here, we're looking at, again, that set builder notation, and we want to make sure that we're using the inequalities correctly. So here we're going to talk about x is such that 2 is less than x is less than 7/2. These are parentheses, so these are less than, not less than or equal to. Negative infinity is less than x is less than or equal to, bracket, negative 3 and then put the, whoops, not parentheses, put the braces there. Put the braces here. We're going to go from negative infinity is less than x is less than or includes is equal to 0. Braces, 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 and braces. So here we're going to have negative 8 is, well, that's infinity. Negative 8 is less than x is less than negative 2. That's going to be exclusive. There's no filled in circles. Notice how our inequalities are always less than, 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 less than. That's how we're going to do that. We're going to read that from left to right, just like we're going to read our graphs when we're dealing with that in 2 dimensions with our functions. All right, so domain and range, I've already talked about this, and in Algebra 1, Chapter 5 is really where you engage with that content in your middle grades work or your high school work. But it's kind of glossed over, and rightfully so, because in that class you're focused on graphing lines. Is pretty much what you do. That's most of the graphing that you do in that whole first semester at the high school level, or the kind of the whole year in the middle school level. And so, so domain and range for those linear functions are kind of all real numbers, right? You can have any x and you can get out any y. It will go from negative infinity to positive infinity on the x. It'll go from negative infinity and positive infinity on the y. And so let's think about what domain is. So this is kind of a formal definition. It's the set of all possible inputs for a relation. What are the x values? The x values are our inputs. Now, the question that you want to ask yourself when you're looking at the graph is how far left, that's going to be your minimum x value, your min x value. You want to think how far right, that's going to be your maximum x value. And then you want to also consider, sorry for the writing here, consider any excluded values. So you might have a situation where you have some excluded values if you have a function that is maybe like a rational function where there's a variable in the denominator. Well, we can't have a denominator equal to 0. Or you're taking a square root or an even root, and you know you can't take a square root or an even root of negative numbers. And so we have some limitations for how we, for what values of x we might be allowed to input into a function. Now, like I said, most of the functions that you've dealt with to this point are just all real numbers, right? You've got lines, you've got absolute values, you've got parabolas, and so there's not really much to worry about as far as those inputs are concerned. But that might be an issue for some of our conversation. The range is all the possible outputs, like what comes out. And so you put numbers in, your x values, you get out y values. And so you want to think about, okay, what are those y values that come out? What are the y values? How far down does the picture go? That's your minimum y value. How far up? That's your maximum y value. And then you might want to ask the question, consider any excluded values. Is there anything that is left out that y is not allowed to equal? And sometimes you'll see that when you're graphing, but if you're just looking at an equation, it might be a little more difficult to manage that. So consider your x and consider your y, consider your domain and your range, how far left, how far right, how far down, how far up. Because we are going to be describing our graphs in terms of those values. And we're going to be describing them as intervals, all right, just like we discussed. So here, do your best drawing of this. If you care for these x, y's, there's 0, negative 3. We've got negative 2, 1, positive 2, 1, and you got a U-shaped graph there. You'll see another one at negative 3, 6, and positive 3, positive 6, if you're graphing that. But basically, we're going to find the domain and range here for example 3. Well, your domain, folks, is all real numbers. All right, it's all real numbers. This will go all the way to the left, and it'll have a really high output. This will go all the way to the right, and it'll have a really high output. These arrows mean that this goes on forever and ever. So it's not just as far as our picture goes. Well, our picture only goes to like 2 and then maybe almost to 3, but we know that there's a point at 3, 6, and we know there's going to be a point at whatever for these other inputs and outputs. So we know that even though this looks like the arrow's just pointing up, we can notice that it's going infinitely to the left and infinitely up. So we would say that the domain, another way to say that is that x goes from negative infinity is less than x is less than infinity in braces, or we can do it in interval notation where we go from negative infinity to positive infinity. That would be all ways that we could write our domain. all right, or ways that we could write our domain. For our range, how far down does it go? Well, it goes down to -3. That's as low as it goes. It will not go down to -4. It will not have another output that's down below here. So we know that it's going to go from -3 on the floor, right? That y is going to be bigger than or equal to, it includes, this is a filled in circle, when we put the dot, it's not an open circle. So it includes that, but then y is going to go up forever and ever towards infinity. So when I'm writing this in builder notation, it's going to look like so. When I'm writing it in interval notation, we're going to go from -3 inclusive towards infinity exclusive. So this is how we would write our domain and our range for this particular graph. Let's look at this graph where we flip that over. Go ahead and give this one a shot. See if you can draw that picture to the best of your ability. All right, you've got this value at 0, 3. You've got this at -2, -1, at +2, -1, and then there will be another one at -3, -6, and +3, -6, if you want to know what's over there. So, can you write your domain and range for that? Do that, please. And if you're wrong, then we'll talk about it. If you're right, then we'll talk about that too. So make sure that you do this one, example 3b. For example 3c, we're looking at a line. This again is all real numbers for x and all real numbers for y. We've already done that. In interval notation, it is this and this. In set builder notation, it's -infinity is less than x is less than infinity. -infinity is less than y is less than infinity. Or we can say that it's an element of all the real numbers at capital R. All right, we'll skip this one for now. Intercepts. The x-intercepts and the y-intercepts. So conceptually, you get that. You're like, oh, this is the x-intercept. This is where it crosses the x-axis. Here's a y-intercept, where the line crosses, or where the graph crosses the y-axis. So these are not new concepts, but the concept that you have of it from Algebra 1 is kind of insufficient for Algebra 2. In Algebra 1, they just said, hey, when you're graphing a line, the y-intercept's the b value. Go to the b value and then rise over run to your next x comma y, and we go on from there. But if you're going to describe to me or to a peer or to a kid in middle school who's learning about y-intercepts for the first time, you say, well, it's the point where the graph crosses the y-axis. And you would use that word point knowing that that point is an x comma y. It's always going to be 0 comma some y value. And when you have y equals mx plus b, it's 0 comma b. But when you have ax squared plus bx plus c, it's not b anymore, it's 0 comma c. And so using that shorthand notation from Algebra 1, Unit 6, when you're first learning to graph lines, it is not sufficient to say that the y-intercept is -3. Because the y-intercept is a point, so it's an x comma y, it's 0 comma -3. The same with the x-intercept. This is where the graph crosses the x-axis. And this will always, the y value will always be 0. It will always be x comma 0, just like this will always be 0 comma y. Sometimes there are multiple sometimes there are multiple x-intercepts. Sometimes there are multiple y-intercepts, but that's only if our relation is not a function, all right? Like we saw in that other picture with the absolute value that was like sideways, right? That's not a normal thing, that's not a function. But if y is equal to a function of x, then there could be multiple x-intercepts, and so be aware of that. These are also called the zeros of a function, all right? And this is a big concept for Algebra 2. This is where does that function equal 0? So we know that we're always graphing y as f of x. The question of a 0, or the x-intercept, is when does f of x equal 0? All right? So I want for us to have kind of this big picture understanding. I know that you wrote all the things down, but I hope that you're hearing and you're listening to this instruction, because this is one of the most formative ideas for what we're going to do in the entirety of this class. And that is solving polynomial equations. All right, that's the kind of the big punchline. We're going to be using graphs to do it. We're going to be using algebra to do it. And along the way, if we can explore the algebra, if we can explore the graphs, then we'll have a better understanding of that work. Here's a real-world situation. It's not a perfectly real-world situation, but it's pretty close, and you can kind of see some average trends. A car starts a journey. They got a full tank of gas. They've driven, again, 0 miles, and they have 16 gallons of gas. But as they drive, all right, it's modeled after this equation, y equals 16 minus 0.05x. So what happens is after they've driven 320 miles, they are now out of gas. You should be able to, without reading this and being like, oh my gosh, this is so hard, there's like all these words and letters and I'm getting so, if we look at the picture and we understand 0,16 means you've driven no miles, you have a full tank of gas, you've got 16 gallons gas. But as you've driven more miles, you're getting less and less gas. There's less gas in the tank, so much so that when you drive 320 miles, you are now out of gas. You've got 0 gallons left. You can have a functional understanding of what these intercepts mean as they relate to a real world situation without doing like hyper crazy mathematics, right? This is just having a basic understanding of what is happening in the universe. And so that may be hard to look at a word problem and say there's too much going on there, but you can probably handle it if you give it a shot. All right, so we'll deal with more of that in the coming days, but first I wanted you to just think about intercepts. We find the intercepts, we find the x-intercepts by saying y equals 0. We'll find the y-intercepts by saying x equals 0, right? Just like our definition stated. So this is really important because we want to be able to say that 0 equals the absolute value of x minus 3. And we want to be able to say that y equals the absolute value of 0 minus 3. All right? If x equals 0 gives me my y-intercept and y equals 0 gives me my x-intercepts, then I should be able to create these equations and either evaluate or solve them as needed. So the algebra 1 here might be a little tricky because it's probably been a while since you've solved an absolute value equation, or been a while perhaps since you've solved a quadratic equation. And so be gracious with yourself, all right? If you're needing more guidance or instruction on something, please let me know. We know the absolute value of 0 is 0. 0 minus 3 is negative 3. 3 is equal to the absolute value of x. How this works is once the absolute value part is by itself, the thing inside here is either this or this is the opposite of that. So if I took the absolute value of 3, I would get 3. If I take the absolute value of negative 3, I would get 3. So what's inside there, the x, either equals this thing or what's inside there equals the opposite of that thing. Well, folks, these are the solutions to those equations. But these are not the intercepts, all right? Instead, the intercepts are x comma that y, x comma that y, x comma that y, all right? These are the y-intercept, the x-intercept, and the other x-intercept. There's 2 x-intercepts. Now, this was doing the work algebraically, but if we were to look at the graph of this function, the absolute value of x minus 3, it would look like this, where we have the point 3 comma 0, where we have the point 0 comma negative 3, where we have the point negative 3 comma 0. All right, and obviously these will go forever and ever. So how you want to explore this is you want to make sure that you can use the graph as needed, but to understand that there's an expectation that you can do the algebra. The graph can be really helpful. So have access to, utilize that grapher calculator so that you can find out where those x-intercepts are, those x comma y's. All right, maybe you have a line. Here we have y equals the 1/3 times x minus 1. If y equals 0, or if x equals 0, we'll have a couple different situations. Here we have the y-intercept is 0 comma negative 1. Here we have the x-intercept. I'm going to add 1 to both sides and multiply by 3 on both sides. I get the x-intercept is 3 comma 0. This again should not be, earth-shattering, mind-blowing. If we were to graph this line, we'd go to the b value at 0 comma negative 1, and then we would rise up 1 and go over 3, and we would find these 2 x comma y's. So this is not, crazy, weird algebra 2. We're just solving when y equals 0 and solving when x equals 0. Last one. Again, to find the x-intercept, we'd say y is equal to 0. We've got 4 minus x squared. Find the y-intercept. That's what happens when x is equal to 0. So we get 4 minus 0. We get y is 4. We have the point 0 comma 4. This one's the easy part. The y-intercept is usually pretty easy because y is usually by itself, right, when y is a function of x. Over here, this is going to be a little more challenging. X squared equals 4. Since this is degree 2, we know that there's 2 answers. When we solved quadratic equations in chapter 10 of Algebra 1 a couple years back, we learned that if we're solving algebraically, we need to take the positive and negative square root to recognize that we can have a positive 2 and a negative 2. So we get negative 2 comma 0, we get positive 2 comma 0 for our x-intercepts. All right? The graph here, if we were looking at the graph, sometimes it's useful to do, we'd have the point, 0 comma 4, and our parabola would go like so, and it would pass through negative 2 comma 0 and positive 2 comma 0. All right, and you might be saying like, well, Mr. Hibbett, that's great when things work out nicely. What if they don't work out nicely? Well, we will be coming to that bridge before too long, all right? So just kind of keep thinking about that. This basically is the end of our first lesson dealing with intervals and making sure that we can acquire or determine intercepts.